there will be heat transfer due to convection. Okay. So, this factor n takes into account this heat transfer, that means the heat transfer due to convection because of the temperature difference between the glass and the surrounding air. Okay. And it can be very easily shown that at steady state the value of n is given by u divided by h naught, where u is the overall heat transfer coefficient, okay, and h naught is the external heat transfer coefficient. So, u is the overall heat transfer coefficient for a flat glass 1 by u, you know that the expression 1 by u is 1 by hi plus 1 by h naught plus delta x by k wall. Okay, this is the resistance of the wall, this is the convective resistance on the outside, this is the convective resistance of the inside. Okay, so you can calculate overall heat transfer coefficient, and h naught is the external heat transfer coefficient. Okay, so if you know the overall heat transfer coefficient, external heat transfer coefficient, properties of the glass, and if you can estimate the total radiation incident on the surface as we have shown in the example, last example, you can calculate what is the solar energy transmitted to the building, okay, through fenestration. Now, what we can do is from the last expression we can write QSG like this. Okay, A and take out A, and you can also take out IT. So, you can write QSG is A into within brackets IT multiplied by within bracket tau plus alpha u by h naught. As I said, tau is the transmittivity, alpha is the absorptivity, u by h naught is your fraction n. Okay. Now, what is done is a single sheet clear window glass. Okay, a single sheet clear window glass is taken as a reference, and a factor called solar heat gain factor or SHGF is defined as follows. Okay, so taking this single sheet clear window glass as reference, we define a solar heat gain factor as this. This is nothing but total radiation incident on the surface multiplied by within brackets tau plus alpha u by h naught. Okay, and the subscript stands for, subscript SS stands for single sheet clear window glass. That means it is for the reference glass. Okay. You will see immediately what is the advantage of defining this. The advantage is that the maximum solar heat gain factor values for different latitudes, months and orientations have been found and tabulated. For example, ASHRAE handbooks gives the maximum solar heat gain factors for different latitudes, months and orientations, etc. So, once you know the solar heat gain factor, maximum solar heat gain factor from the table for a given latitude, for a given orientation, for a given day, then you can calculate what is the energy transmitted into the building if the glass is made of reference glass, because the energy transmitted is nothing but area multiplied by SHGF, right. So, let me show you a typical table adopted from ASHRAE handbooks. Okay, so this table gives maximum solar heat gain factor for sunlit glass, okay, located at 32 degrees north latitude, and the units here are watt per meter square. Okay, for example, for month December, okay, orientation of the surface, if the window is facing north or window is shaded, then you find that this maximum solar heat gain factor is 69 watt per meter square in December, it is 75 watt per meter square during January and November, it is 85 during February and October, and 100 during March and September, like that. Similarly, for northeast and northwest, that means the window is facing northeast or northwest direction, then during December this is the value, during January and November this is the value, February this is the value, like that. Okay, like that it gives the solar heat gain factor, maximum solar heat gain factor for all orientations, for different orientations. Okay, the 8 orientations, and also for horizontal orientation. For all these we are assuming that the glass is vertical. Okay, that means the tilt angle is 90 degrees. Okay, so that means on a vertical wall, right, and this data is valid for 32 degrees north latitude. ASHRAE handbook gives this similar data for other latitude also, for example 24 degrees, 40 degrees, like that, right. So, from this table you can calculate what is the maximum solar heat gain factor. For example, I would like to find out during the month of July, I want to find out what is the solar heat gain factor through a south facing window. Okay, that value is given by 230. right. During a east or west facing window it is 685. Like that we can find out the SHGF maximum. One interesting thing you can observe here is the benefit of putting the window on the south side. As I was mentioning in the last example, you can see that for south side windows, okay, the maximum solar heat gain factor, that means radiation transmitted into the building because of solar radiation through the glass is very small during summer, whereas it is large during winter. Okay. What we want is, we would like to heat the buildings in winter using solar radiation, okay, and we do not want any solar radiation into the building during summer, right, because that way you can keep the building cooler during summer and you can keep the building warmer during the winter. So, using the solar radiation, right. So, this is very beneficial, and this is very beneficial only when you put the windows on the south side, because you see that for the south side there is practically not much radiation during summer, whereas there is a lot of radiation during winter, okay. Whereas for other directions like east west, you find that it is almost same during throughout the year. So, you should not put, you look at the table for east west, the solar radiation is almost constant throughout the year, okay, maybe some 20-30% variation is there. That means you should never keep windows on east or west direction, because on east or west directions during summer you will receive lot of radiation. Of course, during winter also you receive radiation, but not as much as you receive if you put the window on the south side, okay. So, this kind of handbook data are available in the handbooks. Now, this data is for a standard reference glass. How about other glasses? For fenestrations other than the reference SS glass, a shading coefficient is defined, okay. This shading coefficient is defined such that the heat transfer due to solar radiation is given by QSG that is equal to area A, okay, multiplied by SHGF maximum of the standard glass multiplied by the shading coefficient. So, finally, you find that shading coefficient is nothing but the heat transmitted through the actual glass divided by the heat transmitted through a standard glass, okay. That is how the shading coefficient is defined, and the shading coefficient depends upon the type of the glass and also on the type of the internal shading devices, okay. You can use a wide variety of internal shading devices, as you know very well. If you want to shade the window from radiation, you can use curtains, you can use Venetian blinds, rollers like that, okay. So, the shading coefficient depends upon what kind of internal shading device you are using, and it also depends upon what kind of glass you are using, whether it is a double glass or a single glass, etc. Okay. And typical values of shading coefficient for different types of glass with different types of internal shading devices have been measured and are tabulated, for example, in ASHRAE handbooks, okay. So, let me show a typical table. Again, this is taken from ASHRAE handbooks. This table gives shading coefficient for different types of glass and internal shading. For example, for a type of glass, for a single glass, okay, single sheet regular glass, this is the standard glass. If it has a thickness of 3 mm and if it does not have no internal shading, the shading coefficient is 1. The shading coefficient is 1 because this glass is taken as the reference. Okay. So, for this glass the Q is simply A into SHGF maximum that you get from the table, right. However, if you are using internal shading device, for example, if you are using Venetian blinds and the Venetian blinds are of medium type, you find that the shading coefficient reduces to 0.64, and if you are using light Venetian blinds, then the shading coefficient becomes 0.55. If you are using roller shades and dark roller shades, shading coefficient is 0.59. If it is light roller shade, it is 0.25. This is for a single glass. Similarly, for different types of glass, for example, if you are using a double glass, a regular double glass of 3 mm thickness, you find that without internal shading, the shading coefficient is 0.9, whereas for the single glass it is 1, and with the internal shading these are the values, right. Other types of glasses are, you can also have heat absorbing glass of 6 mm thickness. You find that for heat absorbing glass for 6 mm thickness, the shading coefficient without internal shading is 0.7, that means 30% less compared to a regular glass, okay. So, that is how, if you have this kind of information, but then you can select the proper shading coefficient value from these tables, and once you know the shading coefficient value, you can calculate what is the heat transmitted into the building through this glass. Okay. Now, heat transferred through the glass due to solar radiation can be reduced considerably using suitable internal shadings. Okay, you might have noticed that when you are using internal shadings, the shading coefficient is less than 1. Okay, that means amount of heat transmitted is less than 1. Okay, so with this we know, everybody knows that if you want to reduce the radiation, you can simply put a curtain or you can simply use a Venetian blinds. Okay, so thereby you can cut down the amount of radiation entering into the building. Okay, so that is good as far as the cooling load is concerned. Of course, there is a negative aspect to this. When you are using a dark curtain or Venetian blinds, etc., the light that is entering into the building also gets reduced. Okay, if light is not sufficient, then you may have to use some artificial lighting, right? So you have to pay for the artificial lighting. So again, you have to see the balance. You have to balance between the requirement for the light and requirement for requirement for reduction in the cooling load. Okay. And from the type of the sunlit glass, its location and orientation, and the type of internal shading, one can calculate the maximum heat transfer rate due to solar radiation. Let me give a small example. This is a very simple example. We have to calculate the maximum heat transfer rate through a 1.5 meter square area, unshaded, regular double glass facing south during June and December, without and with internal shading. Okay. The internal shading is light Venetian blinds and the location is 32 degrees north, right. So, the data given is we have to calculate during June and December. Okay. So, first let us do the calculation for June. For the month of June, the SHGF max from table is 190 watt per meter square. Okay. So, this is the solar heat gain factor for the standard glass. Okay. Then using the values of shading coefficient from the table, that heat transfer rate is given by this is the expression, Q is A into SHGF max into shading coefficient. If you are not using any shading coefficient, any internal shading, sorry, then you find that area is 1.5 meter square and SHGF max is 190 watt per meter square, and shading coefficient for the double glass is 0.9 from the table. So, you find that QSG is 256.5 watt on June. Okay. And with internal shading, that means if you are using a Venetian blinds, then for the same date, right, you find that the maximum energy transmitted is again given by the same formula, area is same, SHGF max is also same, but the shading coefficient is different now, it is 0.51. Okay. So, you find that the total or the rate at which energy is being transmitted, the maximum transmission rate is given by 145.35 watt. So, from these you can see that with Venetian blinds you can reduce the energy transmitted considerably, it is almost 50% compared to without internal shading. And if you do the same thing for December, okay, so you find that the SHGF max for December is 795 watt per meter square. So, without internal shading QSG is 1073.25 watts, with internal shading this is 608.175 watt. Okay. Again you can see here that because this is a south facing glass, the energy transmitted during summer is much less, whereas it is much higher during winter. Of course, obviously during winter you should not use any internal shading because you want this, whereas during summer you should use internal shading because you do not want this. Okay. Now, let us look at effect of external shading. So far we have been assuming that the window is not shaded externally, that means the full area of the window is exposed to radiation. Okay. But most of the times we find that most of the windows will have some kind of an external shading. Okay. For example, an overhang, right. This overhang provides external shading, that means not all the area of the window will be exposed to solar radiation, part of it is exposed and part of it will be in shade. Okay. So, this will have a bearing on the heat transfer to the building. Okay. So, let us see what is the effect of this. the solar radiation incident on a glazed window can be reduced considerably by using external shadings, for example overhangs. Of course, the external shading can also be provided by, let us say, a tree or an adjacent building, right. So, but here I am assuming that it is based on the overhangs. Okay. So, by proper design of the overhangs, it is possible to block the solar radiation during summer and allow it into the building during winter. Okay. Thereby you can reduce the cooling load and also the heating load. So, what is the effect of overhangs? As we know that overhangs reduce the area of the window exposed to solar radiation and thereby reduce the heat transmission into the building due to direct radiation. Okay. Let me show this. So, this is the window. Okay. So, window has the dimensions of height h and width w. So, area of the window is given by h into w, right, and area exposed to solar radiation is equal to this without overhang. Okay, because the entire area is exposed to solar radiation. But if I am using an overhang with inset, let us say I am using an overhang with inset, this is the overhang with inset, the red hatched portion. So, you have the certain length of it, it has certain width and it has certain depth. Okay, depth of the inset is this, okay, and width is this, right. So, if you are using an overhang, you find that this hatched area at this particular incident, when the sun is at this particular position, this area is not exposed to direct radiation, that means this is in shade. Okay, only this much area is exposed to solar radiation. Okay, that means without overhang, the entire area is exposed to direct radiation, whereas with overhang only the small portion is exposed to direct radiation, and this small portion is given here as multiplication of x into y. Okay, and at any point you can calculate x and y because this is related to your solar geometry. For example, this is related to your altitude angle beta and it is also related to your surface azimuth angle, surface solar azimuth angle alpha. Okay, what is the relation? You can find that at any point x is given by this relation, x is equal to w minus d into tan alpha, whereas y is equal to h minus d into tan beta by cos alpha. As I said, beta is your altitude angle, alpha is your wall solar azimuth angle, whereas w is the width of the window which is equal to the width of the overhang, and d is the depth of the inset, that means this this dimension. Okay. So, if you know the dimensions of the overhang, what is the width of it, what is the depth of the inset, and if you want to find out at any particular incident how much area of the window is shaded, how much area of the window is exposed, then you can calculate it very easily if you can calculate the altitude and wall solar azimuth angles. Okay. Let me give a small example here. We have to calculate the energy transmitted into a building at 3 p.m. Okay, on July 21st due to solar radiation through a southwest facing window made of regular single glass. Okay, that means it is made of the reference glass. The dimensions of the window are height is 2 meters and width is 1.5 meters and the depth of the inset d is 0.3 meters. Okay, now from the given data, that means at 3 p.m. That means our angle is 45 degrees, July 21st you can calculate what is the declination on July 21st, and it is facing southwest, so your zeta is 45 degrees. Okay. So, from the hour angle, zeta and declination you can calculate the altitude angle, and if you do the calculation you will find that the altitude angle works out to be 48.23 degrees. Okay. Similarly, you can also calculate the surface solar azimuth angle which works out to be 39.8 degrees. So, this is the first step, you have to calculate these angles. Once you calculate these angles, you can calculate the dimensions x and y. Okay. X and y is the length and height of the unexposed area. I am sorry, of the exposed area, right. So, x is given as w minus d into tan alpha, where w is the width of the window which is given as 1.5 meter, okay, and d is the depth of the inset that is given as 0.3. Okay. So, you find that x is equal to 1.249 meters and y is equal to h minus d into tan beta by cos alpha, where h is 2 meters, D is 0.3, tan beta is 48.23 and alpha is 39.487. So if you substitute these values, you find that y is equal to 1.562. Okay. So now you can calculate what is the transmitted energy because of solar radiation. So that is now given by SHGF max multiplied by the shading coefficient multiplied by the exposed